So by now, you've seen that there's a lot of different kinds of memory in which we can store data, and they have very different performance characteristics. And when we see such a huge range in performance, that's going to affect how we design systems and how we program. So what we'll do here is introduce sort of an abstract notion of what is a cache and why do we use them and how does it work. We'll give you some of the basic terminology so that following this, we can really dive into how caches work and how we can design them. So I hope by now it becomes pretty apparent that most applications need data, right? And so they read and write data. And we might think of that data as living in main memory, as when we programmed the y86. Or if you've written applications, you might think of that data as living on disk. But fundamentally, when we compare the performance of DRAM to that of an actual processor, DRAM feels pretty slow. And similarly, when we compare the performance of your application running to the performance of the disk, even if it's a flash drive, that's really slow. So if we had to go to that slow memory or slow persistent storage every time we wanted data, things would be pretty awful. So what we do is we introduce a cache between our application and our data because the cache is going to be faster than the data source. And if most of the time when we need data, we can get it from the cache, then we'll get better performance. So from the point of view of the application doesn't really care whether the data is coming from the cache or whether it's coming from the data source. From the application's perspective, there's some amount of data and I want to get it. And if the implementation of that data source can make it come more quickly, great. So the cache doesn't appear to the application explicitly. It's just hidden with the storage to make things look faster. So let's look at how a cache works. And what we'll start with the good case, which is called a hit. So this is when we want to get data and it's in the cache, and so it's really fast. So what happens is the application makes a request and says, please read this item. And then behind the application's back, the cache says, do I have that item? And if it does, it says, great, here's the item. So the application has no idea whether it got the item from the cache, whether it came from the data store. All it cares is that it asked for a data item and it got it, and it happened to get it really quickly. So that's the good news. Now, we don't always get hits. So now we have to consider the alternative. What happens when the application says, please read this item? And the cache says, do I have that item? It goes like, no, I don't have that item. I'm really sad. So in that case, what the cache does without any knowledge of the application is it goes off and it says, psst, I need this data. And it asks the data source for it. And the data source says, sure, here you go. And now the cache has the data and it says, here you go, back to the application. So from the point of view of the application, it doesn't know whether the data came from the cache or the data source or both. All it knows is it asked for the data and it got it. And that's exactly what the application cares about. Okay. And so our goal as cache designers is to try to increase the fraction of the time that we get hits and decrease the fraction of the time we get misses. So in order to do that, let's think about the different cases that can cause a miss. And so we categorize misses into three classes. The first are called compulsory. And they're called compulsory because no matter what you do, you kind of are going to have to pay these misses. And that's the first time you touch data, right? So if you've never touched a data item before, or you've never touched any data item, even like the data item you want, there's no reason for it to be in the cache. So those first loads we call compulsory misses. Now, sometimes an application has a data set that's way bigger than the cache. And in that case, you can't possibly keep all the data you want in the cache. And so sometimes you're going to take misses just because the cache is too small. And those are called capacity misses, right? And the way to think about it is if I made the cache bigger and those misses would go away, that's a capacity miss, okay? Now, the third kind are going to feel a little weird right now, but they'll make more sense as we go on, and they're called conflict misses. And these arise because depending on how we design the cache, it might be that you have two data items and they're only allowed to reside in the same place in the cache. So you might have lots and lots of cache space available, but if you happen to need those two items at exactly the same time or right next to each other, then you'll bring one into the cache. And then when you need the other, you're gonna have to kick out the first one and bring the second one in because they have to go in the same place. Okay, now you're all saying, well, why do they have to go in the same place? Stay tuned. That's exactly what we're going to talk about in the next class. So hold that thought. It's a good question. We'll get there. Okay, but those are called conflict misses. So it turns out that on a cache miss, we have lots and lots of decisions that we need to make. So first of all, when the cache goes to the data source and says, I need this item, the data source needs to decide, like, how much data should I return, right? You asked for 1 byte. Should I really just give you 1 byte, or should I give you more? You might say, well, why should you give it more? It only asked for 1 byte. Well, it turns out that data exhibits what we call lots of different kinds of locality, right? So for example, if you're accessing an array and you access the first element, there's actually a pretty good chance that you're going to access the second element and the third and the fourth. That's called spatial locality, right? Data that is close to each other is sometimes likely to get accessed at the same time. So particularly because we've got such a performance differential between the data source and the cache, the data source often wants to say, okay, you asked for 1 byte, I'm going to give you a bunch of bytes because I think you might use them. So that's a decision, though, that the data source gets to make, like, how much should I give you? And it's sort of a decision that the data source and the cache make together. So that's one decision. Now, I mentioned capacity misses. So there's another decision that we have to make in the cache, which is like, what do I do when I run out of space, right? If I have all my cache has all sorts of good data in it, and you ask for new data, like, what do I do, right? So I have to decide, like, what am I going to kick out? Those are called eviction policies. The other thing I have to decide is, like, where in my cache do I put things, right? So I alluded to this problem of conflict misses, but you give me an item, I have to decide, like, where to put it in the cache. And what we'll see is that in software, we often have lots of flexibility about where we put things. In hardware, we're often much more constrained about where things can live in the cache. And then when I put them in the cache, like, how do I find them later? Well, I guess I better know, like, what's in each cache place. So I need some way of knowing what items are in my cache. So when we design caches, we have lots of decisions to make. And so there are names that we associate with these various decisions. So how much data should I return? That is what we call a block size or a line size or a cache line size. But that's what we mean when we use those terms. And we'll talk about that in just a minute. What do I do when I run out of space? Well, that's what we call this eviction or replacement policy. I need to evict somebody from the cache or replace that item in the cache. And then these questions about how do I know what's there or where do I put things, those are all cache organization issues. And so we're going to introduce terms like cache sets, cache indices, and cache tags that will help us decide how to do that. So this is sort of where we're going and what you'll be getting in the future material. So before I wrap up, I want to focus a little bit on this idea of the block size or the cache line size. So let's think about this. This becomes most clear, I think, when we think about persistent storage. So most persistent storage devices have like a native data access size, and it's often about 4 kilobytes. So if you want to read only 1 byte from a file that you've stored on disk, chances are the disk is going to insist on giving you 4 kilobytes, even though you only asked for 1 byte. So when we build a cache for something like a disk, we're going to build that cache to respect the fact that the disk is going to give us 4 kilobytes no matter what. It just can't give us data in any smaller unit. So therefore, when we build a cache directly on top of a disk, we often organize that in terms of 4 kilobyte blocks. Now, hardware caches also have a native cache size. So a typical cache size in hardware, cache line size, I'm sorry, is usually on the order of maybe 64 bytes or 128 bytes. And the idea here is that we know programs exhibit this spatial locality, that they access data close to each other. So when we put something in the cache, rather than just bring one thing in, since we're paying some overhead to go get something off the lower level storage, whether it's main memory or the disk or whatever, we're paying a cost to go get it. And there's sort of a fixed overhead and then a per byte overhead. And the fixed overhead is usually the big part. So if we're going to pay that fixed overhead, it is advantageous to read in a bunch of data. And that bunch of data is the cache line size. So in hardware caches, what you'll see is that when you ask for 1 long and we have to go to memory, we might bring in like 8 longs or 64 bytes worth. Okay, so that cache line is a really fundamental characteristic of the cache. And that is going to drive a lot of the decisions that we make about how to manage the cache. So hopefully you have sort of a high level picture of what caching is, the kinds of problems we're going to need to solve, and then you'll come into class and we'll start solving them and we'll give you lots of practice doing that. Okay?